Alright, we have a couple of examples for you today on the docket. The first one, we have a single square loop of wire. Each side of the square is 5 centimeters, and it is in a magnetic field of 0.16 teslas. We're going to have a look at a couple of different orientations here, and then we're going to find the average induced current as we move from one orientation to another. So for part A, we have the loop perpendicular to the B field. So here is my B field. My loop is pointing like this. So here we're not looking at the area vector, we're looking at the loop itself, and the loop itself is perpendicular, which means the area vector is parallel. I'll label the field here, so this is my B field. Those are arrows, not X's. So in that case, we get maximum flux because the cosine of theta is going to be cosine of 0, which is going to give us 1. So the flux in this orientation is just going to be magnetic field times the area of the loop. Magnetic field is 0.16 teslas. The area of the loop, we're going to convert this to meters, and it's just a square. So we do 0.05 meters squared, and that works out to be 4.0 times 10 to the negative fourth Tesla meter squared, or I'm going to go ahead and use the unit Weber just for fun. Okay, part B, we now orient the loop, and in this case it doesn't tell us the loop, it tells us the area vector. It says the area vector is at a 30-degree angle. Make my field a little bigger here. So there is my loop doing something like this, where here is a 30-degree angle. So in this case we're going to get BA times cosine of 30. And we already calculated BA, so all we have to do is take this answer here and multiply it by cosine of 30, and that works out to be 3.46 times 10 to the negative fourth Webers. So a little bit less than before, which is what we expected, because as you tilt this loop, not as many field lines will be going through it. For part C, we're going to have to find the induced current, and first of all, we're going to find the induced EMF, which is going to be negative. There's only one loop, so we don't have to multiply by n. We want the change in flux over time, and since we're just interested in average, it's okay that we don't know the instantaneous values of these things. Essentially it becomes delta over delta. So that's going to be our final flux minus our initial flux. Our final flux, let's see, we start at B and end at A. So this is our final value. So 4 times 10 to the negative fourth minus 3.46 times 10 to the negative fourth. And divide that by the time it took, the 0.14 seconds. And that is going to give us an EMF of 3.828 times 10 to the negative fourth volts. Now if we want to convert that to current, we need to take into account the resistance in our loop. So we're just going to use V, or E in this case, equals IR. We want to solve for current, so it's going to be the EMF that we just found divided by the resistance, 3 point blah 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 divided by 0.012 ohms, and we find a current of 0.032 amps, or 32 milliamps. Alright, one last example. Here we've got a coil. We know a handful of quantities, its size, magnetic field, all these things. And we're going to pull this coil out of the field. The reason why we have to have an external force is once this end leaves, when the whole coil is in there, if there were a current, there would be a net force of 0. But once this side is out, you're going to have a force on this side and not a magnetic force on this side. So you have to apply a force to pull it out. Alright, so part A, we want to find the rate of change of flux in the coil if we're pulling it out of this magnetic field in, where's our time here, 0.1 seconds. Okay, so we need to find the initial flux. Again, we're going to, I guess here we're just finding the rate of change of flux for part A, not relating it to the EMF quite yet. So that's going to be, that's a T there, so it's going to be final minus initial. Well, the final is when the whole loop is out of the field, so that is 0. The initial flux is going to be BA cosine theta, and theta is 0 once again. And the area vector is pointing in the same direction as the magnetic field. So we just have B times A, so 0.6 Again, we've got the same size loop as before, but we need to convert that to meters. And then we divide this by the time, and this time we yanked that loop out in 0.1 seconds. So we end up with 0.015 Tesla meters squared, I'll stick with those this time, over seconds. So that is the average rate of change over that time period. Part B, we want to find the EMF and the induced current, so this is pretty similar to what we did before. Well, the EMF is just N, well, we have a negative sign in there, N d phi dt. We already have that part. This time it's not a single loop, it's 100 loops, so we need to just multiply this guy by 100, throw in a negative sign. We get negative 1.5 volts is our induced voltage, and then we want to find the current. So similar to before, it's going to be the EMF divided by the resistance. And where is that resistance hiding? Here it is, 100 ohms. So we're going to divide by 100, and we just multiply by 100, so we're back to the 0.015, but we have changed our units in the process. We're now in amps. Okay, part C, we want to find the energy dissipated in the coil. Well, energy dissipated, one way to find energy is to do power times time, because power is energy over time, so we can multiply the time over here. Power in an electrical circuit, you have a variety of different expressions you can use for that. Probably the most straightforward is I times V, and then we can multiply that times the time. We've got I and V right here, so 0.015 times 1.5, and then the time is that same 0.1 seconds, and so this is going to be 0.00225 joules. Okay. Now, as far as the negative sign, if we're talking about the energy required by an external force, it's going to have to put in positive energy to pull this thing out, so I just went ahead and ignored that negative sign, because that just has to do with the direction it's going around the loop, which is fairly arbitrary anyway, so as far as the signs are concerned, not arbitrary for the actual direction. Alright, so there we've got the energy, and part D, we want to find the average force, so we can use work equals force times distance, if we're just dealing with averages anyway. So the force is going to be the work over the distance. The work done is this energy amount here. The distance is this 5 centimeters. That's how far it took to pull that thing out of the magnetic field. Again, we're going to convert to meters, and we end up with 0.045 newtons. And that's it. See you next time.